Good morning, ladies and gentlemen, and welcome to our webinar on large-scale biogas production from agricultural waste. We hope you will find this subject of interest. At the end of the presentation, we will have a question and answer session where attendees can ask questions on any items of interest. There are two methods of asking questions. The first is to use your control panel to raise a digital hand. If we see a hand raised, we will enable your microphone so you can speak to both ourselves and the other attendees. The second method of asking a question is to type your question into the question box on your control panel and we will read your question out. The presentation will last for approximately 30 minutes. We have allowed a further 10 minutes for questions, but if there is interest, this part of the webinar can be extended. The main language of this webinar will be English. This slide summarizes the key messages we intend to communicate with this presentation. It is our view that cost saving, revenue generation, and obtaining a reliable power supply are the primary drivers for implementing such biogas projects. First and foremost, people build systems such as these to reduce their operating costs and strengthen their bottom line. Unsurprisingly, that is the primary objective. Another key objective is to ensure that power is available when it is needed. Factories function badly when they are subjected to random power outages. Nevertheless, an objective of increasing global importance is that of environmental impact reduction. People are concerned about the environment and they do want to reduce environmental impact. There is a limit to how far you can go with this objective financially, but when it is combined with sound commercial reasoning, it is an obvious plus. Another key message we hope we will communicate today is that well-planned biogas projects are entirely bankable. As we know, banks are not in the risk business. A bank's risk from a well-planned and executed biogas project is as good as zero. Well-planned projects benefit from all of the acquired learning that has taken place over the last 20 years and applies it to the specifics of new situations. This leads to reliably operating biogas facilities, creating added value for their investors. The final message is that there are several ways in which biogas can be used to create added value. This added value can enhance the final net benefit for all of the parties involved. In terms of economic opportunity, on-site power production is, again, the major source of economic benefit. For example, the use of biogas can significantly reduce the cost of site power for the operation of the facility hosting the biogas project. The second commercial incentive encountered is the possibility to produce power and export it to the grid. This option has been somewhat less attractive over the last few years in countries such as Indonesia, but there is a hope that the situation will soon change. Where an adequate feed-in tariff is paid, such projects can be built to supply power to a local network. Steam production is possible where biogas can be fed directly into a boiler. In actual fact, there is minimal modification required to convert a diesel or biomass-fired boiler to accept biogas, so the fuel may be used in existing boilers with minimal technical intervention. Another potential use of biogas is as compressed biomethane. Here the methane component of the gas may be used as a vehicle fuel. This possibility is especially of interest where a vehicle fleet is involved, running within a prescribed area and returning to base regularly. In terms of environmental contributions, these are clear. Greenhouse gas reductions are achieved by not releasing methane into the atmosphere. Increasing renewable energy capacity will, in many locations, offset either coal or diesel, another environmental benefit. Waste minimization and pollution control may be important, subject to the feedstock type and the facility location. Most mills already have pollution control facilities in place. However, feedlots may benefit from anaerobic digestion to convert a discharge problem into an asset. Anaerobic digestion will reduce the amount of lagooning required to achieve a discharge consent. Finally, an often important environmental benefit is that odors can be controlled by covering a lagoon and capturing the gases, and hence capture and reduce odors that would normally have been released to atmosphere. Gas production can be an asset for a great many different types of industries and businesses. Agricultural industries such as palm oil mills, cassava mills, pineapple processors, and other agricultural facilities where there are large organic waste streams may be suitable for biogas production. Industrial applications include, for example, pulp and paper production, where waste from the pulp process may be used to produce biogas. Wastewater treatment plants are well known as a source of biogas. Landfills also produce a great deal of biogas. Finally, the food and beverage industry can produce biogas using the wastewater emitting from the production facility. The sorts of feedstock that we are all familiar with include palm oil mill effluent, POME, cassava mill effluent, animal waste from pig, cattle and chicken farms, organic food waste, Napier grass, and a great many other organic waste streams. In many situations, an environmental problem can be converted into a valuable revenue-generating asset. To give an idea of the order of magnitude of the contribution that can be made by biogas, we can use the example of palm oil plantations in Indonesia. Indonesia produces to the order of 36 million tons per year of palm oil. This would lead to the creation of approximately 100 million cubic meters of palm oil mill effluent per year. Taken as a whole, from such a flow of POME, to the order of 1 gigawatt of continuous electrical power can be produced. This is by no means insignificant and would be a meaningful contribution to Indonesia's power requirements going forwards. The following typical example is given to demonstrate the quantity of biogas that can be produced from a typical palm oil mill. There are many rules of thumb employed in the assessment of biogas production. From POME, we have used 0.6 cubic meters of water per ton of full fruit bunch. COD, chemical oxygen demand, is a commonly employed measure of how much carbon is in the wastewater. For POME, this measure can be variable from mill to mill. A range of 60,000 to 120,000 milligrams per litre of COD is typical. Mills themselves range between 45 and 90 tons per hour of fresh fruit bunch, although there do exist smaller and larger ones. For the purposes of estimation, a figure of 0.25 kilograms of methane is taken as being produced per kilogram of COD that is removed from the wastewater. A mill rated at 60 tons per hour with, say, 75,000 milligrams per litre COD would be able to produce 845 cubic meters per hour of methane. That is enough to generate 3.4 megawatts of electricity on a continuous basis. Slide 7. Taking the previous example further, for the same mill, this amount of methane production, if used in a biogas engine, would avoid the release of 90,000 tonnes per annum of carbon dioxide equivalent. This is different from certified emission reductions, but it is a measure of the amount of methane that is being consumed in the gas engines. In terms of diesel offset, 3.3 megawatts would require approximately 20 tonnes per day of diesel. This would add around 18,000 tonnes per year of CO2 into the atmosphere. If the electricity were fed into the grid with a grid factor of 0.5 tonnes of CO2 per megawatt hour, this gives a saving of around 12,000 tonnes of CO2 per year. CER's certified emission reductions are a measure of the net greenhouse gases saved from being released into the atmosphere. For a project of this nature, CERs would typically be into the order of 50,000 per year. However, CERs have fallen into disrepute because of the price collapse that occurred about 10 years ago. The key objectives in the construction of an anaerobic digestion system are to maximize the biogas production through design optimization, maximizing mixing and using retention time and having control over the pH, ideally with minimum operator intervention. One would like to see the project delivered rapidly and on time, which means concentrated project planning and developing professional troubleshooting capacity. It can reasonably be expected that there will be difficulties. The overriding requirement remains to maintain product quality. This means that focus on materials, component selection, construction management and supervision are all critical to ensure a successful project. This slide presents a quick overview of a biogas feed train. The means of production and processing, as well as the use of biogas, are shown here. There are many different types of anaerobic digester. I will discuss such basic types in a little more detail later in the presentation. Biogas can contain hydrogen sulphide, which is a highly corrosive gas, carbon dioxide, which is not particularly corrosive but dilutes the methane, particulates and moisture. In some cases, oxygen and other trace gases may be present. The feed train is designed to process the biogas into conditions suitable for use in the specific equipment to be employed. In this chart, biogas flows firstly to the hydrogen sulphide bioscrubber. Removing H2S at the start of the feed train protects all other downstream equipment. Carbon dioxide may be removed, if necessary, by a number of techniques. Here we show a water scrubber. Blower skid introduces the pressure that extracts the gas from the anaerobic digester, draws it through a bioscrubber and delivers it to the point of use. Typically, biogas will be at a slight positive pressure as it emerges from the anaerobic digester. A chiller will be required to remove moisture if there is not to be condensate collecting at low points in the gas pipework. From the chiller, the gas can go directly to the biogas point of use, or there may be a further requirement to process the gas, for example with a granular activated carbon column, which can take out certain trace gases. Siloxane is another gas which can be quite damaging, so removing siloxane from biogas is sometimes necessary. A final particulate filtration prior to biogas usage is usually advisable. The range of possible uses of biogas include electricity generation, compressed biomethane, steam and heat. Anything you can use natural gas for, you can use biogas for. Looking more specifically at the main process equipment involved in a typical factory farm-scale biogas production system with a covered lagoon, we have the following. Wastewater is passed from the mill to the pump pit. The pump pit buffers and stabilizes the flow into the anaerobic digester. An important option with cassava is to use wet cake or filter press cake within the anaerobic digester. In the case of tapioca, this can enhance gas production quite significantly. Taking a typical organics bioreactor configuration, we have a carbon dioxide stripper and a recirculation point at the feed inlet, which we refer to as the combined structure. This unit helps control pH and mixing of the whole system. Next, we have a covered lagoon, and as a part of the covered lagoon, we have an optional biomass filtration system designed to help retain biomass within the reactor. It may be desirable or even necessary to have a suitable aeration system, such as a sequencing batch reactor, to obtain a compliant discharge with low BOD/COD concentrations. On the biogas side, the gas passes through a bioscrubber, a gas dewatering system, a gas blower, a particulate filter, and in this case, onto a gas engine. A standby flare is required for times when the gas engine is not operating. With regards to the anaerobic digester, there are 4 possible options available that we will consider here. There are, in actual fact, many different types of anaerobic digester, but these are the 4 principal ones being generally applied. The dry cell anaerobic digester is, as the name suggests, not suitable for low solids liquid waste streams. It is ideally suited for low moisture content organic waste streams such as the biomass fraction derived from municipal solid waste or dry crop waste such as vegetable waste or corn cobs. The covered lagoon, that is the original covered lagoon with internal baffles, has been largely superseded in the market by the covered lagoon bioreactor. In the covered lagoon bioreactor, systems have evolved and developed to give better sludge management, improved gas production, and an overall generally better performance. The continuously stirred tank reactor, or CSTR, is usually built as a circular steel tank. These are encountered where available space for the reactor is limited. The CSTR has a shorter retention time and therefore may result in a lower gas production. The upflow anaerobic sludge blanket, or UASB, is well suited to waste streams which have a high dissolved solid organic component. The UASB does not like to have settleable solids pass through it, as these can precipitate out and block the flow paths. In the case of palm oil, for example, it would not be suitable because the particulates in the flow would clog up the system very quickly. Here we have an example of a palm oil mill anaerobic digester. This particular reactor has a capacity of 60,000 cubic meters and is working with the effluent from an 80 ton per hour mill in Kalimantan. The POME has a flow rate of 1,152 cubic meters per day, and it is producing 70,000 cubic meters of biogas per day. In this particular case, there's no bioscrubber and there's no biogas dewatering plant. Biogas is fed directly into a boiler. If it were connected to a power generator, it would produce the equivalent of 7.5 megawatts of electricity. This relatively high figure comes as a result of a very high COD content within the POME at this particular site. Here we have an anaerobic digester working with a cassava mill. In this general case, the rule of thumb is that the carbon within the liquid waste stream from the cassava mill is usually adequate to produce enough electrical power to run the mill. This mill was experiencing regular interruptions to its power supply. With the use of a biogas system, it was able to be self-sufficient in electrical power. In this facility,
we have a 50,000 cubic metre lagoon that is processing the wastewater from a 200 tonne per day cassava mill. The lagoon can produce 19.2 thousand cubic metres per day of biogas, which is enough for 1.9 megawatts of electricity. In this case, the wet cake is not being added to the lagoon because that would produce excess power, and the mill has no method of using excess power. The objective was to stabilize power to the mill and no more. Should more power be required, the wet cake represents an opportunity to be developed. This is a site in Sulawesi designed to operate with cassava waste. We can see here a 75,000 cubic metre lagoon under construction. As you can see, this is a fully lined system to prevent any possibility of local water contamination and general leakage. The internal architecture, as shown, is in the process of being installed. The system will have pipes running along the base of the lagoon to enhance mixing and sludge control and general biogas production efficiency. This system will take 3,000 cubic meters per day of wastewater and will produce approximately 45,000 cubic meters per day of biogas, enabling it to generate 4.5 megawatts of electricity. Again, this power is solely to run the mill and to ensure reliable power is supplied to the mill's daily operations. I will not go into a comparative analysis of all of the many different types of bioreactor in this presentation. Here we are focusing mainly on the covered lagoon bioreactor. The pluses of the covered lagoon bioreactor are that the cost is relatively less than the alternative option. It is not difficult to construct, although factors such as the rainy season and access do present challenges. Geosynthetic covers are readily available. It is a very stable process with a high internal reaction inertia, and the long retention time leads to a high conversion of COD to methane. The negatives of such a facility are that cheap covers can reduce the lifespan of the cover. This is, in fact, a simple relationship between quality and cost. Good quality usually costs more, and as we know, only quality is truly sustainable. Poor design can lead to solids and nutrient accumulation. We have seen in certain situations where the bioreactor has filled up with solids. In such a case, it would be necessary to lift off the cover and re-engineer the internals to excavate out the accumulation. One thing that is unavoidable is that a large footprint is required. So if you are short of space, a covered lagoon bioreactor is probably not the right solution. Here we have examples of hydrogen sulphide bioscrubbers. They can actually be vertical or horizontal, but people tend to prefer the vertical tank as it requires less installation space. The hydrogen sulphide bioscrubber prevents corrosion in downstream equipment. Hydrogen sulphide is an acid gas and will quickly damage boilers and gas engines unless it is removed or unless great care is taken in its use. The bioscrubber also reduces hazards to health. Hydrogen sulphide is a highly toxic gas. Comparatively small amounts can kill you outright. 800 ppm is the lethal concentration for 50% of humans for 5 minutes exposure, LC50. Concentrations over 1000 ppm cause immediate collapse with loss of breathing, even after inhalation of a single breath. Removing hydrogen sulphide from biogas reduces emissions of sulfur dioxide from all combustion equipment. The bioscrubber also reduces noxious odors. A typical bioscrubber can remove 98% of the hydrogen sulphide contained in biogas. A biogas dewatering unit is an important component when using biogas in a gas engine. It reduces the moisture content of the gas down to manageable levels. Typically, you will want a relative humidity at a maximum of 80% at 40 degrees C. This limit can vary from engine to engine and application to application. The biogas dewatering unit removes the moisture and then reheats the biogas to drop the relative humidity. It will also filter the biogas so that particulates are removed prior to the burner or gas engine. Gas blowers come in many different shapes and sizes. Here we have a series of 3,000 cubic meters per hour gas blowers, each rated at 450 millibar pressure. 450 millibar is high for a typical biogas utilization system, where 300 millibar would normally be adequate. In this case, the higher pressure was required because of a long pipeline to the point of use. Biogas flow rates can vary from 50 to 20,000 cubic meters per hour or more. Once again, there are many different options available for gas flares. The unit on the left-hand side with the two gentlemen in blue is what we call an open flare. This arrangement is perfectly acceptable for use as a standby flare for an anaerobic digester. The flame burns out in the open and there is no reliable means of measuring destruction efficiency. The unit in the middle is fitted to a plant in Turkey, where the requirement was to hide the flame and to maximize methane destruction efficiency for a CDM project. The units on the right-hand side are located in Australia, near Melbourne. They were installed close to a housing estate where there was an absolute requirement to avoid the visibility of flames and to minimize emissions releases. This project at the Puchong landfill site near Kuala Lumpur has an open flame elevated flare with a visible flame. This unit was used as a standby flare, in this case supporting a landfill gas power station rated at 2 megawatts. We can see two 1 megawatt Jenbacher gas engines behind the flare and the fuel skid doing the chilling, the gas filtration and the pressure boosting of the gas for use in the engines. Several basic options for use of biogas are pictured here. The first and the most widely employed use of biogas is electricity generation. Here we see a picture of a 1 megawatt gas engine installed and running on biogas. The second image shows biogas as a source of heat. Biogas can be used more or less interchangeably with natural gas, except for the fact that the calorific value or the heat content of the biogas is less than natural gas, so the flow rate needs to be higher. This may mean a requirement to increase pipe sizes and control equipment for biogas. In this particular diagram, we see an economizer preheating the water going into the boiler. So here we are making maximum use of the heat from the biogas. A typical biogas boiler is shown in the third image. This is a package boiler rated at approximately 6 tons per hour of steam. Finally, something which is extremely attractive and hopefully will become more commonly employed is the use of biogas as a vehicle fuel. This technology has been implemented quite widely in many countries. In other countries, it is still early days for this technology. In time, this technology may become more widely deployed. It is certainly a good solution for fleet vehicles where there is a source of biogas and vehicles round trip regularly back to the same starting point. Working in remote locations presents many challenges to contractors.
In the case of biogas construction associated with the mill, this often means that the mill is in a remote location where access conditions are challenging. Accidents and errors occur. You always need to be careful about when the rainy season falls to make sure you're not trying to work with soil when it is raining heavily and regularly. Social issues also need to be borne in mind, as local people do not appreciate being taken for granted. Great care is needed to ensure that neighbours understand what's going on and to win their support. And finally, the great challenge in all such projects is that of the unforeseen event. Even with the best planning, there will always be hiccups. It is necessary to be ready to work with local people who can overcome them. These two graphs present good performance over a period of time for a covered lagoon bioreactor. This information was gathered by a gentleman called Tycho Cohen, who was one of the founding inventors of the technology involved. We were privileged to work with Tycho over a number of years. The COD removal efficiency, as you can see, is 90% or above. The organic loading rate, that's the rate at which the organic material in the lagoon is removed, is quite high for a covered lagoon. A UASB may be considerably higher than this, but then a UASB requires a lot of attention and also the removal of insoluble solids. The particular arrangement of the covered lagoon provides substantial process inertia, meaning that it can take big knocks in terms of feedstock contamination and still perform well. It can also be operated by a competent technician and does not require a chemist to assess what is going on. Recent technical advances have led to higher organic loading rates and better general performance. As with everything, it is a matter of seeking continuous improvement. The waveform recirculation system leads to higher conversion rates and a higher bacterial retention. The control of pH with the non-chemical acid control is an important development and avoids the need to store sodium hydroxide or lime on site. In normal operation, it is not necessary to add chemicals. Enhanced mixing through recirculation dynamics and pH control are both functions delivered by a combined structure, which ensures such a system can be controlled in one location. A very important attribute engendered from the use of all of the above is that sludge production is minimized. In the case of the system monitored by Tycho Cohen, presented in the previous slide, no sludge removal was required for a period of 3 years and possibly longer. After 3 years, the detailed monitoring exercise was ended. Looking briefly at the subject of finance, the capital cost of such a system will be in the range of 4 to 5 million US dollars for a 3 megawatt plant, including the gas engines. The range of costs is a function of factors such as access, feedstock quality and quantity, and that sort of thing. Operating costs can be quite variable, but 175,000 to 200,000 per annum is typical, including the operating cost of the gas engine, which is the most expensive item. Revenue is subject to whether electricity is exported or used to replace diesel power. It may be to the order of 2 to 3 million US dollars per year, giving a simple payback of circa 3 years. Revenue as a ratio of the capital cost and the operating cost can make this an attractive investment. Bankability is a measure of how reliable and risk-free a project may be considered. The term bankability derives from the fact that banks who lend money are not in the risk business and therefore do not accept any risk. A bankable project is a project which contains no risk at all. In the case of biogas projects, the technology is no longer considered a risk, as there are several hundred such systems in operation in, for example, Southeast Asia. The feedstock quality and composition are no longer considered to be risks, as many feedstocks are well characterized and understood. For effluent, there must be a long-term and inexpensive outlet, but again, for most agricultural situations, the effluent is not an issue. It may be returned to land as a fertilizer or treated in an extended lagooning system. The ultimate test of bankability is the quality of the use to which the product is put. There must be somebody to use the energy. If it's self-use, then clearly energy will be assisting the financial viability of the project providing the organic carbon used to produce biogas. If the energy goes to grid, such contracts are normally considered to be bankable, as operators can expect payment according to the terms of the contract without interruption or delay. There are various methods for financing such a project. The generally preferred method is that the owner of the bill pays for the plant and has it delivered on a turnkey engineering basis. Where there is an interest in third-party finance, several structures are commonly encountered, such as build, own and operate, or build, own, operate and transfer, or even design, build and operate, where the equipment is actually owned by an outside investor but is designed, built and operated by a contractor on the basis of specific terms and conditions. Simple leasing is another commonly encountered option. Then we have many different hybrid commercial relationships which can be developed, such as joint venture, partnership, equity loan, etc. What will the future bring is a question that has been asked through the ages. With regard to global biogas, the big question mark that we all have to address is what impact COVID-19 will have on the world and on global trade. There is every reason to be optimistic that, after the passing of COVID, markets will rebound energetically. Although the oil price is currently exceptionally low, this cannot be expected to last. Oil producers will be looking to recover their losses. The simple way they can do that is by pushing the price of oil back to a higher level. Having seen the impact of their disagreement over price fixing, it is to be expected that oil producers will now seek agreement at every opportunity. Diesel power replacement is likely to remain an attractive option despite the current low oil price. Producing reliable power supply for self-use will also remain an attraction. Whether or not greenhouse gas mitigation becomes an attraction again is yet to be seen. There is some suggestion that the carbon market may become stronger in the future, especially now that after COVID, we have all seen the impact of reduced carbon emissions from the lack of commercial activity. There are many people interested in seeing this continue, albeit with clean technology rather than with no activity at all. Thank you, ladies and gentlemen, for your attention. Now we will open the floor to questions from the audience. To ask a question, you can either type in your question or you can raise your electronic hand and your microphone will be activated so you can ask your question. So, any questions?